Thank you all for coming, and also special thanks to the organizers for making this meeting a reality, and to see a very congenial community all working to address the problem of non-equilibrium phenomena and the role of interaction of matter with quantum photons. Many things has been already discussed by previous speakers. Jung has done a very exciting presentation of what are the role of correlations. Then many others have been discussing things of materials in cavities. Then there will be a little bit of repetition, but I want to give you a different angle of what you can do and why we want to do it, okay? And then let me just give you a cartoon that something that we did with Mohammed and Andrea, but this is to put where we are and what we wanted to do, okay? And then you might think why I'm doing that. A typical cartoon of the things that you do in non-equilibrium phenomena or looking for hidden phases of matter has been running for the last even 20 or more years in this bottom part of the box, in which you have electron correlation, which is materials which could be weakly correlated or strongly correlated, and then you have an intense laser, which is classical field, that you apply, and then you keep increasing the intensity to drive what Andrea was presenting, nonlinear phononics, or any type of electron dynamics in your system. Then most of the physics that you have here, which are from the metamaterials to light-induced superconductivity and more, is a classical understanding in which you treat classical fields of interacting with electrons and phonons. Okay? Then let me go to the other stream, which will be the stream of quantum optics, in which the quantum optics do not care about materials. The only thing the materials is something that provides you the interaction between your photons. And then you can do a mapping of that physics into what is the same type of concepts, but now with bosons. You have a correlation between bosons, condensates, and so on and so forth. Okay? Then there are those two communities, they've been living sort of in two different areas of the world, talking little between them. No? And this part of the workshop is how we make the two communities talking. And there is a wealth of new plethora of interactions and phenomena that is happening when you have a strong interaction, which are with correlated photons and with correlated electrons. No? And that's what we want to explore. How much we can get is a little bit to be seen, and then how much you can realize experimentally is an open question, because this is, as was said, a field mainly driven by theory. And that's what I wanted to tell you. Then basically is, can we go from the phenomenology of laser-induced physics to cavity-induced or environment-induced, which is how you can do this mapping between what you will call Floquet engineering or cavity engineering. Okay? This was introduced in some previous talks. Martin and Michael has done some work, but I want to give you a flavor of what this entails. Okay? The main idea is the following. In laser-induced physics, what you have is something that you drive the material with an external field, and then you have high intense, and you can stabilize a non-equilibrium phase while you are applying the laser, usually, and then it's short-lived. Then the question is, could we design an environment such that the non-equilibrium state that you reach with the laser is what you will call a ground state-like solution, which will be a long-lived. Okay, and this will be the main aspect. Just to give you a flavor of what and why this could be the case, let me just guide you with two equations to understand what is the analogy between Floquet and cavity materials engineering from a different perspective of what was presented before. Let's take Floquet engineering, and you have a monochromatic drive, no? But this is something that is trivial. Then you have the full many-body wave function. You can keep it for independent electrons or for interacting, and then you do a Fourier series in time of your wave function. This is an exact representation of your many-body wave function. Then you can plug it in the Schrödinger equation, and then basically what you end up is a sector which was with the eigenvalues of your matter system, which are duplicated with replicas of 1 photon, 2, 3, 4, -1, -2, -3, -4. This is like AC Stark ladders that you have in your system. And then to make things easier, let's assume you are in the dipole approximation. This doesn't matter, it's just to give you the analogy. Then you will connect the sector +1 and -1 in those layers, and the connection is the intensity of your laser. And then you have both the P dot A term and also the A squared term that connects your transition with the -2 and +2. Okay, that's the equation that you need to solve, and that's the beauty of Floquet, because you are making a time-dependent problem and a static problem that you can solve. Okay, and you have the stationary solution. What happens if you do cavity materials engineering? Then let's take a Duncan expansion of your many-body wave function, and now I take it in terms of Fock states and the same matter states. Then I subsume the coefficients in the Fock, okay? If you want to put it, this one only will be a change of matter. If you do the same analogy and plug the equation, you get the eigenvalues of the matter system. Then you get the same thing with M, but then you have the 0-point motion of the photons included, acting on the wave function, and then exactly the same thing. It's ±1 photon being absorbed, ±2 photons being absorbed in the system. Okay, then here, just to give you an analogy, because I am abusing the language, the A is the intensity of your classical field. The A here is the light matter coupling, and it's not the same quantity. But if you were thinking that you can have the same values in the cavity, big if, then those two equations, they look very much the same. Okay? Then what is the difference between cavity and Floquet? And it's what I told you before, is that the value of M, in the case of the cavity, is positive. It's 0, 1, 2, 3. And in Floquet, you have it positive and negative. If you just type it in a matrix form, you will have that the Floquet is one of the corners, the cavity, the Hamiltonian is one of the corners of the Floquet. In many cases, they will share similar eigenstates and eigenvalues, but it's not guaranteed that in all cases you will get the same. Okay, I wanted to tell you this because I will show you in a minute why I am saying that, and then you will see what is the difference between having classical driving and quantum driving. Okay? That's the whole setup. Then this is what we wanted to do, and this was the motivation. There is many things being done. Okay, no, I don't get it. In the Floquet type of approach, which is stabilizing metastable states into driving. This is the typical case in which you stabilize a saddle point. And then what you want to do is how I do this in the cavity. In the cavity is by introducing another dimension which comes from the cavity photon that introduces this zero mode, like a X mode in your system that stabilizes in a Mexican hat potential well the ground state of your system. Okay? And this comes from that previous map. Then this is what was the motivation, and then you come up. If I'm able to control the vacuum fluctuations surrounding a given material, and I get the relative large light matter couplings, I would be able to do what you do with light-driven phenomena, plus new aspects. And this is quite interesting because in principle this will be the ground state of your system. Okay, and then this comes for, once you believe this is what we want to do and you buy it, then you can ask, can we modify the electrical conductivity, the superconducting temperature, the magnetic order, and so on and so forth. Everything that you've been discussing in all these light-driven phenomena, but from the perspective of vacuum fluctuations. Okay? And that's what I would hope. I will show you two cases of this if I reach that part of the talk. But before getting there, I took some notes of them with you. First is what are the values that we are having here, because we need to be realistic. One aspect is if you take the lamp shift, you see a real estimation of what is the normal light matter coupling for a single atom or molecular emitting. Then basically take a number, it's 10 to the minus 6, 10 to the minus 5, you choose. But this is something that you can measure, but is very small. And then this is what you expect will not lead to major effects, neither in chemistry or in solids, if you keep it that value. The other aspect is that you have these Casimir forces, which is the attraction between the two plates, metallic plates, which is also small but visible, and then but is of the same order of magnitude. It's only that it's bigger because you have basically can be understood as plasmons moving in the two plates that create this attraction. And then the question is, can we enhance this coupling? And this was presented also by Jun and others, is that the coupling scale as the one of the effective volume. This is not the Fabry-Perot volume, it's the effective volume for the light matter coupling. That could be in plasmonic cavities another value. The other thing which is really important is that the coupling is collective. You have many emitters that will help you to enhance the coupling, and this is where solid-state physics plays a role, because you have many of those collective motions, which is, you have a ferroelectric transition, it's a macroscopic motion, you have dipoles moving all over the place, and you don't have a single dipole per unit of volume, which is good for those transitions. And something that you have to keep in mind, we don't have electric field, real electric field, in principle. Okay? This is if you were working at zero temperature. At finite temperature, there are radiative fields that will also populate your cavity models. And that's where we are, no? But now, let me just give you a little bit of, as was presented, a case that you believe that quantum fluctuations do change the material's properties. There is the typical case that you all know, is if I take vibrational excitations, that you can write the Hamiltonian of an electron-phonon coupled system with the electronic degrees of freedom, your phonon bath, and the electron-phonon coupling, which is a dipolar linear coupling between electrons and phonons. This is the typical Hamiltonian for the electron-phonon that people has been used. If you take it for molecules, then you get basically that you have the 0-point motion of the molecule, the higher order, and then you have all those motions in the harmonic potential that are not equally spaced. There is an anharmonicity, which makes you the difference between the 0, the 1, the 2, the 3, coming from anharmonicity. And this is important to keep it because you have interactions between the 0, the 1, the 2, the 3, the 4, just due to the anharmonic potential. Then, if it's harmonic, the potential that gives you this coupling is sort of boring because you will get many of the physics doesn't fly. Then you need to have an harmonicity or non-linearity. Let's call it non-linearity in this sense. Once you keep that, the first thing you get is that 0-point motions make helium, which you can do it for helium, superfluid at t equals 0. And this is one of the cases that you can do whatever you want, but the system will not solidify due to vacuum fluctuations. Again, this is typically the idea. And then if you compare, this is the Hamiltonian for electron-phonon systems. The Hamiltonian for electron-photon systems is exactly the same, mathematically. The only thing you change is the creation of the phonons by the current in the matter, which could be dipolar. Then basically you could have all these phase transitions that you have due to phonons now realized in the photon sector. Okay? Then this was to tell you that even if the coupling is weak, as long as you have fluctuations that are bigger than a given amount, which is in this case the fluctuations of the ions are bigger than the crystallization length, the system will change phase. Then now what you have to do? What is the analog of the photon? The photon will be the expectation value of the fluctuations of the electric field. And then you have here many things that go with E squared, which could be Raman modes if you want to couple two phonons. You can have ferroelectric transitions on ferromagnetism in systems with a large spin orbit coupling. And those are the systems that we are going to address with Kavli. And this was basically my part of the introduction to motivate that there is room for doing it, and there is potential to achieve that coupling and that modification. Then, as I wrote to you, this is the many-body Hamiltonian in the non-relativistic case for the electrons and the photons. This is in which you have subsumed the A squared term here, and the longitudinal part of the interactions here. This is what also Marco was presenting in his talk. Then I'm just highlighting here the transverse part, but all the longitudinal effects will be included in the W. I'm showing this because the idea is how we are going to handle the problem of having electron-electron interaction, electron-photon, and electron-phonon. No? And then this is what we did. And then before getting there, what I wanted to tell you is, in spite of the fact that this is a very complex system, you can prove mathematically that this is a self-adjoint Hamiltonian. And the most important thing for a computational scientist is that the Hamiltonian is bound from below. This thing that takes you, that seems trivial, is what makes you that there is a ground state. Then you can really design variational methods to look for the ground state. You might think this is trivial. There are many Hamiltonians that mathematically you cannot prove they are bound from below. In particular, relativistic QED is not bound from below. Okay, then this is important for you to keep in mind. And then what we did is just, now it's a question of flavor. If you like to do it in many-body framework, couple cluster, wherever you want for the electron-electron interaction, fine. What I'm discussing here is only the electron-photon interaction. Okay? And in that sector, what you can prove is that the full many-body wave function, the evolution of the many-body wave functions of electrons, photons, and phonons, can be uniquely determined by knowing the current, which is a three-dimensional quantity in your system, time-dependent, and the transverse vector field. This could be small, in many cases will be 0, but then it's basically that the current and the vector field determines the equations of motion. And now I will show you, this entails that you have a set of self-consistent Maxwell, we call it Kohn-Sham-Pauli equations, to deal with the interacting system. This is important because at the end of the day, after all that, I told you you end up in something you were expecting, that you have to solve Maxwell and Schrödinger. No? But now comes the difference. The Maxwell that you have to solve is a Maxwell for n interacting photons. And then for the electronic part, what it entails is that there is a new potential that appears, which is, this is an abuse of language, but then you call it photon exchange correlation potential, which is the interaction between the matter and the photons in your environment. And then what you could do is go back to what people did in the DFT framework in the 60s, which is Walter Kohn and Shell here, and then you do the LDA approximation. What means LDA? Is you have an homogeneous electron gas, and you apply a mode in the cavity. You can put as many modes as you want, and then you solve this with auxiliary quantum field Monte Carlo, no? And then you can get the solution of that problem. It's basically, it's time-consuming, but it's something you can do. And at the end of the day, you can map the potential in terms of the density of your system. Okay? And you can do it both for the electron part and the correlation part. That's the functional that we will use in the calculations I will show you later. And now you can think of doing GGA expansions, adding correlations at different levels. Then it's up to us to do. There is one thing that is important for you to keep in mind. In contrast to the electron-electron case, that is strongly beyond non-independent particles, photons, if there was no matter, are basically independent. Then the independent ground state of the photon-photon interaction would be a good starting point. And then the matter is introducing the photon-photon interaction. That's the reason why you will see the LDA works much better for this photon-matter sector than for the electron-electron. Okay, and then let me go to the case of the comparison between light-driven and cavity-driven. If you want all the equations, how these look like and how we solve it, happy to show it. I just removed everything. Then let me just go to, okay, yes, now.
So the Hamiltonian you wrote
yes.
Like a matter Hamiltonian, or did you adiabatically eliminate?
No, but
not this
yeah.
one, of course, the other one.
No, this one has the...
No, this is clear, what you call the...
this one,
yeah.
only the matter Hamiltonian.
Only the matter.
But
and then you have a Maxwell's equation with
a many-body
polarization.
interaction, a many-body Maxwell equation solver. Okay. Then you solve with Riemann-Silverstein. Then there is two solutions. One, this is for the current part of the Hamiltonian, and then there is another that gives you the vector field and has to be solved self-consistent. It's only that the equation looks awful for the Maxwell. I can show it to you.
That's why you don't.
Then I decided to remove it, but it's possible. Okay? And this is what is called this back reaction. And then if you take this theory and then you put it in an empty cavity and you put a material in the middle, you get the renormalization of the cavity mode due to the screening of the system. You get all these retardation effects and magnetic effects. But you only get that if you let the Maxwell field change as the matter density and current change. Then what people tend to do normally is you solve the matter, get the current, the density, you plug it in the Maxwell equation and solve the modes. That's what you do. If you do that, there is nothing interesting. Okay? Then the interesting thing comes because you have this self-consistent loop. The other one is what you do in linear response theory, which you can explain many things, but it's not what we are aiming at in this particular project. Okay, let me show you this case, and this is, the first part is well known, in particular because our chairman has proposed that many years back, is this beautiful thing of having graphene. Many people have discussed it, and I apologize for the repetition, but I hope, bear with me that there is a different aspect to it. Then there is the gap that you open here is first topological and is proportional to the intensity of your driving field and inverse proportional to the frequency of your driving. Okay? And okay, this proposal was nicely demonstrated experimentally by James, which is here in the audience, which the ultra-fast transport method that he just presented the other day. Then there is a consensus of that you have this sort of interplay between topology and the interaction of light. This is classical light, and then you can enhance this phenomenon. Before getting to the whole, I wanted to tell you that don't think that all the contributions for the James experiments, they are coming from topology. That is what you would like. There is a contribution from topology, you cannot deny the fact, but there is a major contribution from nonlinear optical effects, which is population imbalance. And then the competition between the two gives you the total spectrum. Then now you can ask yourself, is there any way that I can make this small and this bigger? Then no one tells you that you cannot do it, no? And then this is the case, and then let me just guide you, and then you will see in a minute why I'm doing that. Then you have graphene, you have this gap when you do it with the polarization field, and then you can decide, okay, let's do optimal control. How I turn on a laser, and for how long, such that the population of the top or the bottom, you choose the one that you want to populate, is maximized, okay? Then, if you do that, what you realize is, okay, let me just, what you get is a very simple shape of the potential, which has a single driving circularly polarized frequency, which will be the stationary solution after the race time. And then you can see that for short time, this is the period of your frequency, you get the population of the two states, which is half-half, and that's the reason why it is not relevant. And then you can make this one populated with one, okay? And this, you can control it. And then the outcome of the laser is what you would expect, is a mainly one single circularly polarized frequency, what you would expect. And then just is to tell you that the method works and give you, but this one has 99.9% fidelity on the flock. Okay, there is one aspect that you should know. It's impossible to get 100%. You can demonstrate mathematically that is not achievable, but you can get 99. Now that you get to this point, you can ask, why I stop there? Why I don't do flat band physics that everybody wants to do? And then what we did is, let's put as target, instead of having a gap, a flat band in a small portion of the Rubio in zone. That is the one that you get with Moiré physics, which is very small. And then you can get what is the potential. And then you see that only with three frequencies alternated and with dephasing, you can realize that flat band. Okay? And this is just classical optimal control, and it's not something that you cannot achieve in the lab. You can even think of changing the mass of the electrons, and then going from negative to positive to zero. Then you can do all the change and do the inversion. And still you can do it with a small number of frequencies. The only thing that dictates one or the other is the relative phase between the frequencies. Okay, said that. Now you see the point is that this, if you think of the cavity language, means I have to have a cavity which is chiral with the first mode populated. I have to have a cavity with three modes being populated or four modes being populated with a relative population that is dictated by this intensity. Okay, and that's the thing that you could use this. Okay, I will not get to that.
I'm curious about the optimal control. How sensitive is it to shifts in the parameters if you have the frequencies, the amplitude is a slight bit off of your recipe, or the phase is a slight bit off?
It's very sensitive. The only thing is that you put as constraint, what I did is you have a main driving laser and only multiples of high harmonics of that laser. And then you can define what is the width and of the pulse that you want to put, and then you take it from experimental data. Those are the constraints that you put, and that's what limits at the end the success of how much you can make it flat, how much you can turn it around. And it's not that you can do it in all the Rubio in zone, because if you want to do it in the whole Rubio in zone, you need to have basically unrealistic shape of the laser.
So the size of the Brillouin zone is given by the wavelength, or 1 over wavelength. So it's a very...
It could be, no, but then it's an interference phenomenon. If you see it here, sorry, let me see if I know that for this thing is really small. Because it's just the size of that is dictated for how many frequencies you want to put in your laser, which tells you how many oscillations you include. If you include higher and higher harmonics, I can make this larger and larger. Not infinite. Okay, don't. It's really small, eh? It's really, you just see the number, it's 10 to the minus 3. And I was not trying, it's just really small flattening. Okay, this is the thing, and then what we was discussing is now we are in the point of optimizing the cavity to achieve that. Okay, let me just go to the results of the engineering. Then this is with classical fields. Oh my God, I'm done and I didn't get to anything. This is what you want, is with cavity fields, which is the circularly polarized. The linearly polarized is what you don't believe. And then I want to tell you that even if you have a single cavity mode with linearly polarization, you do open the gap. And then if you are having a linear isotropic, which is what you have in classical fields, you don't open the gap. And this is what you get in Floquet. Okay, let me just take the equation, and what you do is what I wrote you before in the Floquet space, and then you get this zero, the ground state part of the Hamiltonian, the Hamiltonian with the 1 photon, 2, and so on and so forth. And I will do the high frequency limit in which you can diagonalize this Hamiltonian by blocks. Okay? And then if you do it, you end up that the effective Hamiltonian just taking the first order. Doesn't matter if you include more, okay? But this is good. You have this combination of 0 and 1, and then you can put as many photon modes as you want. Okay, go ahead.
Is it possible here to introduce a non-thermal states?
Yes.
Or general thermal states, or being a variational approach, you would work only?
No, you can introduce non-thermal states.
So how would you do it? Like you would put boundaries?
With the density matrix. It's a density matrix formalism with realizing the density. Because this goes on the matter part, and this will not affect anything that I'm telling you here. If you want, we can discuss, but it's not connected to the wave function. You can do it with the density matrix of the photons, of the matter. What I wanted to show in this case is if you take this high frequency limit and you were putting classical fields, you get a local interaction, and this is Aoki-Oka result, that they give you the local field with interaction. This is diagonal. Then is what they have, and then in order for this term to open the gap, you need to break time reversal symmetry. However, if you just look to this equation and you have the photons, there is another non-local interaction, which is two-body. And this two-body interaction is between momentum in different sites. And this just comes from the fact that you have this multi-mode structure of your cavity. Okay? And this is not the same, but this two-body interaction looks like the Coulomb, and then you are going to get some spontaneous symmetry breaking of the interaction, which means a renormalization of the hopping between nearest neighbor and next nearest neighbor. Okay? Once you do that, this is what you get, and this is what I wanted to tell you today, and then I will skip the rest, is Aoki-Oka result will be the dashed line, but when you have cavity photons, which is quantum limit, the gap is modified by the quantum effects. Then this is the limit if classic laser implies that you have focus states with high occupation, then you have to do it. But we are in the other extreme, in which the focus space is basically with 0 photons. And in that case, the gap is renormalized. And it's interesting because the renormalization is not small. It can go as a factor of 2, as you compare the local versus non-local. The dependence is exactly the same that Oka got. It's linear and quadratic with the intensity. This is good, and it's, of course, topological. And now comes the surprise, which is what I wanted to tell you. If you do it with linearly polarized light. Here at least you have a cavity mode, or many cavity modes. You can put all, as long as they are with a single polarization. Okay? Which will be a one-dimensional cavity. In this case, this is the solution of the model with classical light. There is no way you will open the gap, because you didn't break time reversal symmetry and it's classical. And then only you shift the K point, if you wish, with an electric field. But in this particular case, you will get this line, which is topological, and then open the gap in one direction. And this is the interesting thing, and I will finish, is that the gap is 0 in the classical field, and then increase with the light matter coupling, and of course, also reduce with the frequency of your cavity. Go ahead.
Okay. Quick question. When I look at these bands, there's a discontinuity. I mean, it's derivative discontinuity. This looks very strange.
Yeah, it's the same discontinuity that you have in the very phase when you go from here to here through the Dirac point. Have you ever, if you look to the wave functions, at the Dirac point is discontinuous.
The wave function, yes, but I mean, even your energy levels, the bands are not smooth.
No, if you look carefully, they go this and then they smooth out. Okay.
But it's like a kink.
It's a sort of kink. It's just.
Okay.
But it's really interesting because this, you can prove this is a reminiscence of the discontinuity you have in the Dirac cone.
Okay, I need to understand this better. Yeah, that's true.
I have it, okay. But
I have a question too.
Of course.
Is that coming from the not enough like meshing in the momentum space?
No.
Like why
No.
you're seeing this?
No, this is not a numerical error. You can prove analytically that that's what you should get.
I also don't understand how you're able to break the time reversal symmetry.
You are not breaking time reversal symmetry, is what I told you. You don't break time reversal symmetry. The key point is that you break sublattice symmetry. The non-local interactions that you introduce, what they do is they introduce the hopping between AB and then AA in the second order. They are different due to the nature of the cavity mode, which is a multi-mode structure. This spatial dependence of the interaction makes the hoppings different, and then makes a difference between A and B sublattice. Once you break that symmetry, you open the gap, as you are in the case of Bn. It's only how much you break the sublattice symmetry.
So the other value is the symmetry.
Yeah, the rest remains the same.
The K prime value is the same.
Yeah.
So the opening is only at one value or in both of them?
In two. In one direction, but in other directions you will not open. It's only you are opening it in one direction. Okay. It's difficult to see, but that's what you get. It's really interesting, in my opinion, because then if you did have a 2D cavity, just to give you that this is not a magic effect, and you have the 2D, all of the same you get what you are doing, which is there is no gap opening. Okay. It's only when you have all your modes polarized in one direction. No. I was going to show you this now. Then now you might think, oh, is this interesting? Okay. Now comes the interesting thing, because one-dimensional cavities are complicated. I'm sorry, I wanted to show you superconductivity, ferroelectricity. I don't think I have time, but I finished with graphene. Okay. Then what we can have, instead of having a circularly polarized mode, I can have an elliptical mode, no? And then this is really nice, because if you do the elliptic solution, it's also analytic, and this will be what the gap depends on the ellipticity, going from circular to linear, just to put you the length. Then you go from a value to a 0, and then in the cavity is twice bigger, as I told you before, due to this non-locality. But now comes the beauty. If I have two modes, and the strength of the coupling in one direction is bigger than in the other, in X bigger than in Y, which means the AX and AY are not equal, in the classical field, you don't open the gap. But in the quantum, you have a gap opening that goes to 0 as this gets to 1. When they get unequal, it's 0. When they are not equal, it's finite. Then even in a 2D system, you will open the gap, and this is just a quantum effect of the Fock space. If, and I can tell you now, you were assuming my Fock states are populated with a high number, which is you are making the quantum description as close as a classical description of a coherent state, the gap will go to 0. Okay, all this is not published, then it's just to discuss. Go ahead.
In this case, is not topological, right?
Okay, now comes. No. Okay. As everybody likes topology, okay. Then basically what you'd say is for the elliptic case, it's topological, as you would expect, because it's a linear combination, then you get the topology. In the case of the two linear modes, there is no topology being involved. I can show you how the wave function changes, the discontinuity. This is irrelevant. It's non-topological, as you would expect, as in the case of the linear, and here it is. John, sorry.
So maybe I'm a little confused about the method, I guess, but when you say you want to look at the quantum limit of few photons versus the classical limit of many photons, how do you actually implement that if the method is solving for the ground state or everything self-consistently? So how do you actually tune then independently the photon number?
The photon number, the way you tune it is because you can assume whether the initial state that you're having has 0 photon number occupation, 1, 2, 3, or...
Does that mean that the system then has degeneracy, like the functionals degenerate somehow?
Yes, exactly.
Okay.
Okay, I didn't show it to you because that limit of getting coherent states with Fock states in the computer is a pain in the neck. Because you don't reach, never, because the matrix becomes impossible to diagonalize at a given point. That's the reason I didn't show you, because it was creating more discussions than solving my problem of telling you that the classical limit will be achieved. Okay.
So in the classical limit, you do not have a band gap for linearly polarized light. In the quantum limit, you do.
You do.
At what number of photons does the gap close?
That's something what we are exploring now. These results are last week. Then it's not. Then I cannot tell you. I think as soon as you start getting few, immediately the gap close. The few is what I cannot tell you. Few is few, but we're not talking about thousands of big numbers.
But for one photon, you still have the gap?
Yeah, with one photon you still. With two photons you do. With three, I don't know.
I mean, of course, it's super naive picture. Could I think of it as, let's say, if I were to think of a linear band, just a linear band, and I would sort of apply, and if I apply DC field, then I get my Wannier-Stark ladder. Then if I now apply a classical AC field, then I would not see anything. But now, in a sense, could I sort of think of it as, okay, now you've quantized kind of the field that you have, because you are now in unit of photons. Is there any analogy there that you could
I think the analogy goes that if you have a classical field, the way you describe it, acting on the Dirac cone, what is happening really, even if you have an oscillating field, is the fact that the Dirac cone is being pushed away in the Brillouin zone. This is known by electron phonon and also electron photon. Then you can, and it's really beautiful because if you go to many papers in the past, they say electric field opening of the gap in graphene is wrong because they see at K, but the gap is close another part in the Brillouin zone. That's what, however, then you have all these momenta, and then the fact that this is for a small case, and those ones you don't have it with the one photon case, and then eventually you break that symmetry and you open the gap.
If I may, so what is the scale for, let's say, so the correct unit is the gap versus vacuum field, basically. Yes. And what is that number?
I told you I was not going to give it. No, there is some estimation, but I think still is, if I tell you one number, most likely will be wrong. I was trying to get it yesterday night, but my postdoc refused to give it to me, then I cannot give it to you. But it's a scale, in this case, the gap. The question is whether that number is realistic in experiment or not. I'm not going to state that this is the case. But if you get enough light matter coupling, the beauty here is with these asymmetric cavities, which will be elliptical, or the ones that you will have an intrinsic opening of the gap of the. Of course, you might be interested in the case that is topological, but if it's only two independent ones, will be not topological, but you have the gap.
How long do you have for this superconductivity part? Like, I'm also very interested in that.
Okay.
Yeah.
No. Okay. I skip the 2D. Okay. The 2D is basically to control them. Just to keep the message as vacuum fluctuations, what you see is the Casimir force, what introduces a force that between two plates, no? Due to the different density of states outside and inside the cavity. If you have now a 2D material, you can think that you have two cavities. One is your external one, then you have the two TMDs in between, and then you have different density of states. And then if you do all the math, it entails that there is a force that is acting between the two layers and makes the interlayer distance smaller. Which, if you take molybdenum ditelluride, that is the one that many people like, which is ferroelectric, you will change the ferroelectricity in that system. And it's a trivial experiment that can be done at the level of what you do with Casimir force. Okay, this is what I wanted to tell you about ferroelectricity, but let's go to superconductivity, and you stop me any time. There are few proposals. All of those proposals are from people in the audience, and I will not basically there to discuss the ones of the other people. Okay, we did one with electron phonon with Michael, then there is the one that was discussed by Markov and Dolina, which is the electron-electron ampere coupling. This is very unlikely. Let's put it that way because it's very small. He showed it, and I don't need to discuss. And then there is the one that John Curtis with Mohammed and Victor proposed of additional coupling. All those are in place. Then I'm not claiming that one is better than the other, it's only that this one is very small. And if you remember the first part of my talk, the interaction between matter and 0-point fluctuations is enhanced if you have nonlinearities. The nonlinearities are intrinsic in the phonon sector. All phonons are, as you were saying, is nonlinearly coupled, more than the photon. Then it's an ideal setup in order to benefit from those nonlinearities. And this is what I thought that the most interesting things to study are BCS superconductors instead of the highly correlated one. Okay? And then this brings me to the cartoon. What we want to see is, can I renormalize the electron-phonon coupling that does the pairing between electrons? And this is not that you are making something fancy. The only thing you are modifying is the phonon frequency and his coupling to the electrons. Okay? And if you saw what I was showing before, this is realistic because it's what is naturally coming into play in these interactions. Okay. And then the other thing that I wanted to tell you is that the mode, which is also what Andrea is doing, that is playing the role is a Raman active mode. It doesn't need to be a Raman active mode. It could be an IR, but you don't need because there is not real electric field. Why the Raman? The Raman is because it's a reader of fluctuations, because the Raman mode goes with the expectation value of the E square. There could be a real E square due to thermal fluctuations, but also the E square of the vacuum. Okay? Good. That's what I want to say. And then what I will show you is how the electron-phonon coupling changes in this system as a function of the light-matter coupling. To a disclaimer, in the paper with Michael, we already got that the electron-phonon coupling was renormalized. But the iron selenide is not a good system because the TC goes linearly with the electron-phonon coupling and inverse proportional to the phonon frequency, which tells that the TC wasn't changed. Then in that paper, we conclude the electron-phonon coupling was modified, but not the TC. However, in magnesium diboride, the electron-phonon coupling goes in the exponential and the frequency in the prefactor, and then a change in an exponential, even if it's small, will change the temperature. That's the whole idea behind. Okay? And then the beauty is that this magnesium diboride, in order to convince you, DFT works perfect. You can predict the inter-sheet coupling between the Fermi surface is connected to those phonons, and then the agreement between experiments and theory has been excellent for the last 20 years. And this is an ideal system in which you believe that everything that we do at the electronic and electron-phonon coupling level should be correct. Okay? And then what we did is exactly this type of calculations in which you take the functional I showed you before. You can compute the Liasberg function, which is the electron-phonon coupling matrix elements in the presence of the cavity photon. It's relatively trivial. And then basically what you do is you compute the total electron-phonon coupling strength, which is the integral in the whole spectrum of the Liasberg function. Okay? And that's what you get if you just plot. In the case of outside the cavity, you get a lambda of 6.2. In the case of in the cavity, you can go to 6.4. No? And that's a modification due to the A to G mode that is displacing the main peak of the electron-phonon coupling. And as I knew I was not going to get here, I have all the slides to show you how this happened. Then basically this is for a strong light-matter coupling, which is 0.2, which is the one that probably Hanan will show you can reach in his cavities. This is the effect you will get, okay? And then we'll scale. Outside the cavity, you have the gap equation closing around 40, it's 30 point something. And then when you have the in-plane cavity mode, you increase by a factor of 5 to 6 Kelvin the TC. Okay? I have to tell you that you might say, this is working for all superconductors? No. We have also other electron-phonon mediated superconductors in which the TC goes down. Okay? Then it's not always going up. This is the particular one in which goes up because it's extremely sensitive to the phonons at K point. This is what is called the non-adiabatic phonons, which are known to be modified by this. Okay? And this is the whole story of the things, and this is, I finish, promise. Then clearly, what I showed you for solids, for technical reasons that I'm happy to discuss with you, we did everything in the dipole, long wavelength approximation, is that because it's not easy to do go beyond. For molecules, we can do it. We can treat, we put perfect cavities. There is no problem to have lossy cavities and incorporate things that Gianmarco was presenting in his talk. And then the temperature and losses is something that is on the way to be done, and it's clearly something that I like is that now you can combine the two things. I can do the pumping of the cavity to enhance the light matter coupling, And then I have a light matter enhanced of quantum fluctuations. And that's what the selling argument is, that we have to play with how quantum fluctuations and light matter coupling and electron phonon correlations dictate the phase diagram of a solid in this aspect. Okay? With that, I think this is the people. Most of them, many of you, are here in the audience, in the cavity. Thank you for your attention.
Thank you. Thank you very much. So,
I just want to have a disclaimer. This is from a nice quote that I like.
Maybe I'll start. Yeah, thank you very much for the talk. Can you go back to the coupling of the cavity to the phonon and just repeat how precisely does the cavity influence the phonon that then goes into the electron phonon coupling? Can you go through that one more time, please?
No, of course. Then in that case, if you want me. Okay, this is one. Maybe I take this one. Downstairs. 1 second. And then we go to the other one. Okay, this is the one that you are asking. Okay, if you go to them, okay. Outside, this is the same equation that I showed before, and this is the phonon dispersion. And you take the E to G mode. If you look, all the phonons around all the areas of the Brillouin zone, they are marginally changed. I mean, you have to put a lens to see. However, the E to G mode changes as a function of the light matter coupling. This is for 3 light matter couplings and goes down. Okay, and this is an off-center mode, because you have to have finite Q to do this coupling. And it can go down by more than 20 centimeters minus 1.
More than 20% of the eigenfrequency. Okay, I see it.
Okay, let me remind you something. There are 2 phonons in potassium doped T60, potassium doped graphene, graphite, and magnesium diboride, which are the phonons close to the K point, is what you call cone anomaly. There is a nesting of the Fermi surface due to the phonons at that frequency. Those phonons can be changed, in the case of graphite, by up to 200 centimeters minus 1, just by doing a small doping or electric field. And that's the reason of all this superconductivity with the lithium intercalated graphite. The only problem is that you cannot increase it to much higher temperatures so far.
Okay, thanks.
Any other urgent questions? No? Okay. So
it's not urgent, but it's a question. Is that okay?
You can ask.
So recently, actually, the student just put the paper on the archive yesterday. We looked at patterned with actually Victor. We look at patterning phonons and see how much that can change TC. And we had a hard time explaining where that is coming from, because once you sum over all frequencies from 0 to the Y frequency, it's really hard to see where it comes from. It's kind of like an overall effect. How can you point, or can you point to the mechanism? Because right now you're saying that my photon is coupling to a specific part of the phonon structure, and that's where it comes from?
No, because this is not only and this was done already many years back. If you just remove from your electron phonon coupling, when you build this Elias-Baer function, the A2G phonon and around a small portion of the Brillouin zone close to the E2G, which is where it gets softer, there is any modification of the TC.
I see.
Basically, what you could do is the opposite. I don't include any phonon, and I just include the E2G, and I get a modification of the TC. Of course, you cannot include only one phonon, otherwise it's, in realistic, you need to...
No, but you have to sum over all of them. But yes, I was wondering whether you can kind of see...
This is a blow-up. It's really a small part of the Brillouin zone, and this is the integration that you need to do. And it's one that it gets really soft. Basically, what you are using is the lowest frequency goes as 1 over omega in this, and then you have the light matter coupling in the exponential. Then the two things go in the same direction of increasing TC.
Can you do both photon and phonon engineering? Cavity for both phonon and photon engineering? So
we could, we did not do it.
I see. I mean, like the formalism allows for that?
Yeah.
Okay,
however, can I say something? The way we compute that, in order to make it feasible, we use the functional that I told you, no? And then this is one of the cases that is a disclaimer. I didn't do the self-consistent coupling to the photon field. Then the Maxwell equations are solved once. Yeah? Then eventually, if we want to do what you want, I have to do the full self-consistency, but it's not that it's impossible, it's I have not done it.
I see. Okay, very cool.
Okay, so in interest of time, let's stop here. So thank you very much, Angel.